Hi, this is Mark Ryman with the Monsanto Learning Center in Gothenburg, Nebraska. Today I want to visit with you about knowing how much water is available to your crops. There's a few really important things to that topic. First of all, I want you to have an understanding of what are the types of soil water. Then, what is the soil's water holding capacity and how much of that is plant available? Other things to think about are there any restrictive layers? What's the potential rooting depth? And what's the maximum allowable depletion that you can let the soil go to for your crop? The first thing I want to visit about is what are the different types of soil water to kind of help you understand the topic. A good way to think about soil water is really in terms of the fuel tank maybe in your vehicle. You've got an empty point representing no water in the soil and a full point meaning that it can't hold anymore. What's a little bit different about soil water than in your fuel tank is that you've got a part that's unavailable. About half the tank, you could maybe say the bottom half, is unavailable to plants because it's just too hard to remove it from the soil. Then you've got that upper part, that's represented by the green triangle. That's really what's available to your plants, and they can actually extract that and use it. It's really that useful portion of soil water. There is another portion of soil water at some points, and that's really saturation. So if you've got a mud hole or some ponding out there, there's almost too much water for the soil to hold, or there is too much. And that actually drains off and isn't really useful to your plants either. When we think about soil water, maybe it's helpful to visualize it. I've got drawn here some gray soil particles, and they're at the wilting point. They're still surrounded by a very thin layer of water, but it's not extractable by the plants. You contrast that with soil that's at field capacity. You've still got some room in there, you've got some air holes, but you've got more of that space filled up by water, and that is plant available. And then you move on to that saturation point where the water isn't useful. All the pore spaces, or most of them, are filled with water. And what this causes is water drains out and you lose it. The next thing I want to talk about is what is the soil's water holding capacity and how much is plant available. And the main factor that we normally talk about in terms of soil water holding capacity is the soil texture. Soil texture is really defined by the different mineral particle sizes that are in the soil. So clay particles are the smallest, and then you have the kind of intermediate silt particles and the much larger sand particles. In most soils, you don't find only sand particles or silt or clay. You get a mixture. And so depending on, what mixture you have, if you've got a high percentage of sand, you have a sand soil. If you've got a lot of silt or clay sand mix, you've got the loams. And then if you have a really high percentage of clay, you're talking about a clay soil. To visualize this soil particle size difference and the influence on the soil, I laid out a few everyday objects. The first one is just the tip of this pen. It represents a clay particle that's about 1 millimeter in diameter. Clay particles are much smaller, but this is just representative. The next thing I laid out, in contrast to that size, is a quarter. That represents a silt particle that's about 80 millimeters in size. So you can see that dramatic size difference from clay to silt. And then the last one's a trash can lid that represents just a medium-sized sand particle, obviously a dramatic size increase, up there to 500 millimeters, or about 500 times the diameter of that initial clay particle. What else you need to think about when it comes to the size of the soil particles is actually their influence on surface area. And the surface area of those minerals is where the soil particle interacts with things like water, nutrients, and gases, other things that can be attracted to the surface of those particles. Think about it this way. If you've got a big cube, let's say it's 4 centimeters on each side, the surface area there is 96 centimeters. Then you take that and you split it up into 8 small cubes, so you've got 2 centimeters on each side. Now what you're looking at is a surface area that's doubled to 192 centimeters squared. Think about that back even further to our relation where we have that 1.0 millimeter clay particle and the 500 millimeter sand particle. What you get in that case is if you were to cut that sand particle, let's say down to 1 millimeters, and it was a cube, you would basically make 125 million particles out of that one sand particle, and you've taken the surface area to 500 times what it is in the sand particle. And this graph really shows off that relationship. of the surface area's effect on plant available water. On one hand, you've got the sands on the left side of the graph that really have a small amount of plant available water. Then you move to the loams, and you get a pretty large difference between that green line, which represents the maximum water the soil can hold, and the unavailable water. So that's where you get that largest distance and the highest volume of plant available water in a soil. As you move into the clays with that higher surface area, that distance starts to narrow up. That red line increases, and you've got a little bit less plant available water in between that wilting point at the red line and the maximum amount of plant available water on the green line. To explain this relationship a little bit further, I took an oven-dried coarse sand soil and an oven-dried silt loam that's fairly consistent with what we have here at the Learning Center, and took 300 milliliters of those and placed them in a plastic cup that I drilled some holes in the bottom of, and then put a filter disc in to stop the soil from running out. The next thing we did was add 150 milliliters of water to each of the soil types. You've got the coarse sand there on the left, and then you've got that heavier silt loam soil on the right. We then let that water drain through for about 24 hours. On the left, you can see the water quickly moving through that sand, and on the right, more slowly through the silt. After 24 hours, we were left with different amounts of water in our graduated cylinders. The coarse sand had about 76 milliliters of drainage at 24 hours, and the silt loam only had about 16 milliliters of drainage at 24 hours. When you actually go through and do the math on it, you can see that the 300 milliliters sandy soil retains 74 milliliters of water. When you calculate out the volumetric soil water content, which is just that milliliters of water retained divided by milliliters of soil, you get about 2.96 inches of water per foot of soil. On the other hand, when you look at a silt loam soil, you can see a pretty dramatic difference. It retained about 134 milliliters of the 150 milliliters of water, and you end up with a soil-water relationship there of about 5.36 inches of water per foot of soil. And this chart just really helps to kind of boil that down. At the top, you've got a fine sand, and that only holds about 1 inch of plant available water per foot of soil. And then at the bottom, at the other end of the spectrum, you've got a loam, very fine sand, a silt loam, holding about 2.5 inches of water per foot of soil. And then in the middle, you've kind of got your sandy loam, fine sandy loam, all those other soil types averaging about 1.4 to 2 inches. It's important to remember that only about half of the water in the soil is plant available, and that's what's reflected here. So the really important question becomes, how do I know what my soil texture is? There are a lot of ways to do it. There's a couple of simple methods. One of those is to actually get your hands dirty and determine the soil texture that way. There's some guides online to help with that. And the other is to use a tool where you can look up the location in a soil survey. A number of precision farming tools and the USDA have some help for this. The other option is to use something really accurate like a reputable soils lab. It's probably the most expensive, or certainly is the most expensive, but it provides you the most accurate results, and that can be very important when you're trying to make irrigation decisions. So in short, take some time to know your soil texture to help you understand if you're farming a silt loam with high water holding capacity, or a coarse sand that you can't count on for much water, or something in between, so you can do your calculations and understand how much is plant available. The next thing to think about in terms of how much water is available to your crop is whether or not you have any restrictive layers. These could be plow pans or some other form of compaction that really restricts root movement and the water moving into the soil, so you have less space to work with in terms of plant available water. To explore the concept of restrictive layers a little further, we set one up. We put a layer of sand in between two layers of silt loam, kind of just to showcase what it might look like in the soil. If you can visualize it, here we're drawing some roots that are going into that box where there's a plow pan. The roots kind of skid along the surface, maybe a few penetrate, but the full volume of soil isn't open for the plant to extract water from. On the other hand, on the left-hand side, you can see that the roots coming out from that plant are unrestricted, and they can utilize the total volume of soil. When we took a little bit deeper dive, we actually poured water into the cups at the top, and they've got a pinhole in them that allow the water to slowly drip in. We let that go for a period of time. After 34 seconds, you could start to see that water move in. At 15 minutes, now the water's about down to that plow pan. At 21 minutes, we actually made it, down to the plow pan, and that's kind of where the water stops. Further on at 25 minutes, you can see the water spread out across the surface of the plow pan, and at 45 minutes, now the box on the left is actually moving down below the plow pan on the right. So it's easy to see how that could influence water infiltration and how less water will be available to your plant roots. The next thing to think about is what's the potential rooting depth of your crop, because that's going to impact how many feet of soil it actually extracts water from. For instance, do you have a corn crop that's maybe fairly deep rooted when it's mature, say something like 4 feet? Or do you have a soybean crop that's maybe only rooting down 2 feet? Or do you have a wheat crop that's somewhere in between? Those are things that you're going to have to look to universities to kind of find, based on your crop species, what your rooting depth might be. The other thing to think about is what's the growth stage of my crop? Younger plants can't explore as much soil, so a V6 corn might only have a root depth of about 1 feet, where a fully mature corn plant might have a root depth, we would say, at 3 feet or maybe even 4 in certain circumstances. So it's something to investigate. You can look at research information to give you a good idea, but you could also, go out there and actually probe the soil to understand where the plants are extracting water from to get that maximum rooting depth. The last thing we're going to talk about is what is the maximum allowable depletion. And that's really thinking about how much water am I going to let my plants extract from that available triangle before we decide they're in water stress and want to irrigate. So when we look at a chart of available water or allowable depletion, you start with 100% at the top, and that's field capacity representing the amount of water the soil can hold. The next area from like 100% to 70% of plant available water, that's easily available water to the plants. It doesn't take much to extract it, and the plants aren't stressed in that range. When you move lower, let's say 70% of plant available water to 30%, that's where water kind of becomes moderately available. You can actually have some plant stress as you move into, say, 40% of plant available water remaining or 30%. And typically, this is the range where maximum allowable depletion is set. For example, for corn, we might say 50% is the maximum allowable depletion at the R1 growth stage. As you move even lower than that down the scale at 30% to 0%, the soil water is severely depleted. You're going to start to show signs of crop stress in this range, and it's really going to start to affect yield. And then as you move into 0, you get to the permanent wilting point. This is the point where your plants have extracted so much water from the soil they actually die because they don't have enough of it to survive on. One of the keys that we see in terms of corn, you'll have a stressed crop, you'll have leaf rolling and things like that, and those signs of stress that can get pretty common out there in the field. To prevent this stress from occurring in the field, it's important to know where you are in terms of soil moisture compared to field capacity. There's a number of different ways of looking at soil water. The simplest is probably the appearance in field method, but it can also be the least accurate. You can do gravimetric or oven drying, which requires taking soil out of the field and drying it to measure soil water. You can use things like electrical resistance, tensiometers, and capacitance probes that actually come in the form of commercial options that are available on the market to help you manage soil water. To kind of show you what the simplest method looks like, that appearance in field, it's simply taking a soil probe out there, pushing it into the soil, and feeling that soil to see how crumbly it is, kind of looking at its appearance, and then the feel to understand how much water is actually available there in the soil for your plants. But any way you do it, you do need to get a handle on how much is there. So the final thing we're going to do is really put it all together and determine how much water is available to your crop and in your soil profile. So we set up a few scenarios. We've got a silt loam soil, fairly high water holding capacity, 2.5 foot of root depth under our corn, 70% of plant available water, and an allowable depletion of 40%. So with that in mind, we go back to that table of plant available water by soil type. We've got a silt loam, and it's got about 2 inches per foot of plant available water. We take that back to the scenario and plug it in. We've got 2 inches per foot of plant available water. We've got a 2.5 foot root depth. So if we multiply those two together, the 2.0 times the 2.5, it actually gives us 5 inches of available water. We've got 70% of that water still plant available, so you've got 0.7 minus 0.4, the depletion, gives us 0.3 or 30% of plant available water remaining. We take that 5 inches times the 30%, and that gives us 1.5 inches of plant available water that the corn can use before we need to irrigate. So now we swap out the silt loam for a fine sand. That gives us about 1 inch of plant available water per foot. We've still got the 2.5 foot root depth. So we take that 1 inch per foot times the 2.5 feet, gives us 2.5 inches of plant available water. We've used some of that, so we take the 70% minus our MAD of 40%, and that still gives us 30% of the plant available water remaining. We take the 2.5 inches times that 30%, and that gives us 75 hundredths of water. So we have less time before we're going to need to irrigate this corn crop compared to the silt loam, even with the same setup. So let's recap the plant available water. First, figure out your soil type. It tells you a lot about the plant available water that could possibly be in your soil. Then determine if there are any restrictive layers. Is there anything that's affecting how much volume of soil that plant can get to? Determine the plant rooting depth to let you know how much or what volume of soil the plant's exploring. Then use a method to figure out the water status of the soil so that you know how much is plant available. And finally, do that math. The math is really what puts it all together and helps you come up with a concrete number that you can use in irrigation scheduling. Thanks for listening. I'm Mark Ryman, and we look forward to visiting with you in the future about irrigation information.
For more information on this topic, you can download the Monsanto Irrigation Handbook for the Great Plains by using the following address. This video was produced by the Monsanto Water Utilization Learning Center.